Hi friend, welcome to Math A to Z. Our today's discussion is on a particular chapter of ordinary differential equation, ODE. Okay, and the chapter is, or topic is, exact differential equation of special form. Exact differential equation. Now, what is exact differential equation? A differential equation of the form f of dny dxn to y x equal to q of x is said to be exact differential equation if we get this differential equation by differentiating from another differential equation of the form this is also a differential equation, but the order of this differential equation is n minus 1, and if we derivate this, then if we get this type of differential equation, then this is called exact differential equation. Or it state alternately as, if we can integrate this differential equation with respect to x, then it is called exact differential equation, and we get from this by integrating this type of equation. Right? Now we understand the exactness of a differential equation by an appropriate example. Consider x d2y dx2 plus 2x dy dx plus 2y equal to 0. This is a differential equation of second order. Now we can write this as okay. From here we get x d2y by dx2 plus dy dx plus, if we take ddx of 2x minus 1 into y, then from this we get dy dx, here 1 extra dy dx, here dy dx minus, and from this we get this result, and it is equal to 0, so we can integrate both sides and we get x dy dx plus 2x minus 1 into y equal to 0. This is equal to c, integrating constant. So this equation is exact differential equation. Now we state a necessary and sufficient condition that a differential equation of the form p0 dny by dxn plus p1 dn minus 1y by dxn minus 1 to Pny equal to R. This is named as 1, first equation. This equation being exact, the condition of exactness is Pn minus 1 dash plus Pn minus 2 double dash minus, that is alternately plus minus to P0 n minus 1 to the power n, where here P0, P1, Pn are all the function of x independently. And here P0n, this is means dn by dxn P0. Since P0 is a function of x, so we can differentiate this n times. Okay, so we name this equation as 2, and this is 2 is the necessary and sufficient condition that the differential equation 1 to be exact. Now we go to the proof of this necessary and sufficient condition. 2. At first, let the equation 1 is exact, right? Then we have to prove this equation satisfied. Now, if equation 1, that is P0 dny by dxn plus 2 equal to R, this one equation, first number 1 equation is exact, then we integrate. Then we can integrate the equation 1 in both sides with respect to x, and we get another differential equation of order n minus 1. Let it be u0 dn minus 1y by dxn minus 1, u1 dn minus 2y by dxn minus 2 to pn minus 1y equal to integration, this is u1, this is r dx plus an integrating constant c, right? Now, since by integrating this one we get this result, so if we differentiate this result, then we also get the result 1. Now differentiate this equation or this relation, we get the first term, differentiating first term, we get u0 dny by dxn plus u0 dash dn minus 1 by dxn minus 1. Integrate, differentiating second term, we get u1 dn minus 1y by dxn minus 1 plus u1 dash into dn minus 2y by dxn minus 2 to differentiating the last, we get u1 into dy dx plus u1 dash into y equal to r. Okay. Now if we arrange this equation as u0 dny by dxn plus here the same term, then we write u0 dash plus u1 into dn minus 1 y by dxn minus 1, and here u1 dash plus u2, into dn minus 2y by dxn2 to q, this is qn minus 1, and this is also n minus 1 and n minus 1, right? qn minus 1 dash y equal to r. Now comparing this equation and the equation 1, we get P0 equal to Q0, P1 equal to Q0 dash plus Q1, P2 equal to Q1 dash plus Q2, and so on. Pn equal to Qn minus 1 dash, and R equal to R, both sides are equal. Now if we put the value of Pn minus 1, Pn minus 2 to P0 in this result, we get the result as Pn, that is Qn minus 1 dash, right, minus Pn minus 1 dash, that is Qn minus 2 double dash plus Qn minus 1 dash. Here Pn minus 1 is Qn minus 1 dash plus Qn minus 1. So differentiating this, we get the result, and so on by putting all the value, and the last value is minus 1 whole to the power n into Q0 to the power n, and putting all this value, we get all the term are cancelled. This term cancelled, this term and the term in the second bracket is also cancelled, and all the term are cancelled. So it must be equal to 0. Okay, so from this result we say that this is the condition of exactness of this differential equation, right? Now we put the theorem from sufficient point of view, that is from only if point of view. Here we take this is correct, or this is assumed here. This is assumed here, and we can show that this equation be exact. Here we start by taking integration as here Pny taking integration, this is dx equal to it be remains fixed. Okay, Pny dy dx equal to Pny dx. This is the first relation. Now we take the previous relation as integration Pn minus y dy by dx into dx, right? Here Pn minus y dy by dx. Then we integrate this. Then we get, by integrating by parts and taking this term okay, this term is the first term and this term is the second term, and we get Pn minus 1 integration dy dx into dx minus integration Pn minus 1 dash, that is the derivative of this term, first term, and integrating dy dx to dx, and here the whole integration. This is the formula of integration by parts, and this gives the result p n minus 1 into y minus integration p n minus 1 dash into y into dx, and we take this is d. Now integration p n minus 2 into d2y dx2 into dx, and all similar manner we integrate this by integrating by parts. Here we get first term as p n minus 2 dy dx, right, minus second term as p n minus 2 dash dy dx into dx. Now integrating again this term and get p n minus 2 dy dx minus p n minus 2 dash into y plus integration p n minus 2 double dash into y dx. Okay, this is C. Now in similar manner, if we integrate all the term and we add all the result, then we get the result as here for every relation there is an integration in the last term only. So we first integrate, so we first write the last term of all the result, sum of all the result. Okay, then we get the first term as integration pn minus pn minus 1 dash plus pn minus 2 double dash 2, we get the in the last relation minus 1 to the power n p0 n times differentiation into y dx. This is the sum of the last term of the all relation, and the sum of the previous term of all the relation gives the result as p n minus 1 minus p n minus 2 dash plus p n minus 3 double dash minus this, and this is into y plus, and similarly we adding the previous term of all the result, we get p n minus 2 minus p n minus 3 dash 2 plus dy dx, and so on. We get the last term of the left hand side is p0 d n minus 1y by dx n minus 1, and the right side is given by integration r dx plus c. Okay, because here is also an integration, integrate r dx plus 1 integrating constant. Now we clearly show that here only one integration remains in the left hand side, and this term cannot be integrated either if we take this term equal to 0. And if we get this term equal to 0, then this is vanished from this side, and we get the integration of 1 as this. Okay, so 2 is the sufficient condition of exactness of 1. And if we consider 2, or if we satisfy condition 2, then we get the solution of 1 as this. And this is also the formula of integration, or formula of evaluation of first integral of this type of differential equation, which is exact. Okay, now we consider here 1 or 2 most important example to clear the theorem. Okay, now we consider the first example as so this is the condition of exactness. This must be equal to 0, and this is the formula of integration. Here we consider an example 2x square plus 3x into d2y by dx2 plus 6x plus 3 into dy dx plus 2y equal to x plus 1 into e to the power x. Right? Then comparing this equation with p0 d2y by dx2 plus p1 dy by dx plus p2y equal to r, we get p0 this, p1 this, p2 this. Now the condition of exactness is, so in particular here the condition of exactness is p2 minus p1 dash plus p0 double dash, that is equal to p2 means 2 minus p1 dash, that is 6 plus p2 double dash, that is 4. So 1 is exact, right? And the first integral of 1 can be taken as this is the first integral of 1. Now the formula is here pn minus 1 minus pn minus 2 to this type of formula. So here the formula is p1 minus p0 dash into dy dx, right? p1 minus p0 dash into, sorry, from we write from here, from the back side. First term is p0 into dn minus 1 into y by dx, that is p0 means 2x square plus 3x into dy dx plus, and the previous term of this is p0 dash, sorry, p1 minus p0 dash into dn minus 2y by dxn minus 2, that is here p1 minus p0 dash into y. Okay, and this is equal to r means to the power x into dx plus c. This is the formula. And if there be third term, then here P2 minus P1 dash plus P0 double dash into y, and here be dy by dx then. Okay, now we get the first integral as 2x square plus 3x into dy dx plus the P1 minus P0 dash, that is P1 6x plus 3 minus P0 dash 4x minus 3, right, into y equal to integration x e to the power x dx plus integration e to the power x dx plus c, that is 2x square plus 3x into dy dx plus 2x into y equal to integration of this is x e to the power x minus e to the power x, that is x minus 1 into e to the power x plus e to the power x plus c, that is x e to the power x plus c, and 2x square plus 3x into dy dx plus 2x into y. Now here we also let this is P0, this is P1, but P1 minus P0 dash equal to 2x minus 4x plus 3 not equal to 0. So this is not exact. And in this case, here this is a linear differential equation in y. So we can solve this type of problem. Okay, now we consider another example. Consider another example as sin x d2y by dx2 minus cos x dy dx plus 2y sin x equal to 0. Comparing this, we get P0, P1 and this is P2. Now P2 minus P1 dash plus P0 double dash equal to 2 sin x minus sin x, okay, and P0 double dash, that is plus sin x. So this is equal to 0. So 1, if this is 1, is exact, and the first integral of 1 is P0 into dy by dx plus P1 minus P0 dash into y equal to integration 0 dx plus c, and this is sin x dy dx plus P0 minus cos x minus cos x, right, equal to c, that is sin x dy dx minus 2 cos x into y equal to c, and this is also a linear differential equation, so we can solve this type of differential equation. Now we consider the last example of this chapter or of this method, and this is the last example of the class. We consider root x into d2y by dx2 plus 2x into dy dx plus 3y equal to x. Here p0 equal to root x, p1 equal to 2x, p2 equal to 3. Now putting in the condition of exactness, p2 minus p1 dash plus p0 double dash, this is not equal to 0. So it is not exact. Okay, and since this equation, the coefficient of all the term is a power of x, is in the form of power of x, so we can take x to the power m as an integrating factor. Now we multiply both sides of this equation by the integrating factor x to the power m, and we get right. And if we compare now, then p0 equal to x to the power m plus half, p1 equal to 2 into x to the power m plus 1, and p2 equal to 3 into x to the power m. Now if we take this as an exact differential equation, because we multiply both sides by an integrating factor, and from the definition of integrating factor we say that this is must an exact differential equation. So we can take p2 minus p1 dash plus p0 double dash equal to 0. And from this relation we get, by putting the derivative of p0 double dash, p0 dash and p0, we get as minus 2x to the power m into m minus half plus m plus half into m minus half into x to the power m minus 3 by 2 equal to 0. Now clearly from this relation we see that if m equal to half, then the relation is true. That is, m equal to half, then this term be 0 and this term be 0, and other value of m cannot this term or cannot the left hand side to be 0. So we must have m equal to half. That is m equal to half, that is root x is an integrating factor. Okay. Now if root x be an integrating factor, then our differential equation becomes, this is half, this is half, this is half, and this is half, and we get the differential equation as x d2y by dx2 plus 2 into x to the power 3 by 2 dy dx plus 3 root x into y equal to x to the power 3 by 2. And this equation must be exact. Now we continue the above process of exact differential equation. We first find the first integral, and then this equation is a linear equation, or if the first degree equation be exact, then we can find the solution of the equation by similar manner. Okay. Thank you. This is the today's class. Thank you for watching. Thank you very much.